Hello everyone, it's Benny, and in this video, I'm going to be showing you how to implement Variance Shadow Mapping inside a 3D game engine. Now, if you want to look at the engine I'm working with, you can download the starting code in the description, and you can also download the finished code in the description, in case you want to, compare or debug or what have you. So, with that, let's go ahead, let's dive in, and let's get started. Now, the first thing we're going to change is in our rendering engine. Right now, we're creating a basic shadow map that's just the depth component. And that's nice if you want to do basic shadow mapping, but we're doing variance shadow mapping. So, I'm going to change the format. Right now, we're storing a depth component. I don't want to store that anymore. What I want to store are two components, a mean and a variance. So, I'm going to have a two-component texture, RG, because those are the two components, and the format's going to be 32F, for 32-bit floating point numbers. So, there. And if you don't have 32-bit floating point numbers, you might be able to get away with doing 16F like this, but I really recommend going with 32F if you can afford it. So, yeah. Now, data we're passing in, again, doesn't really matter because right now we're not passing in anything. But I'm going to change it anyways just to be GL RGBA because, just so we have something to pass in, I suppose. It doesn't matter that much. Finally, the attachment. Right now, we're not going to be rendering just basic depth information into this anymore. We're going to render color information. So, we're going to have color attachment 0 here. And there. And with that, that actually does almost all we need right now. So I'm going to go into our shaders. It's under Res to Shaders. And I'm going to open up my Shadow Map Generator fragment shader. Now before, this wouldn't be used because we were just rendering depth components, and our texture is set to disable the fragment shader if we have depth components. But now we are. So I'm going to change this. I'm going to have it as, well, start off, I'm just going to fill it out with 0, 0, 0. And what I'm going to store is, in the first component, I'm just going to store the depth. Now, technically, this should eventually end up being the average, but in our basic shadow map render, we're just going to start out by storing the depth, like we would in basic shadow mapping. Now, we're not actually going to store the variance in the second component, despite what I've been saying. We're going to be storing the information we need to calculate the variance. And in that case, that's just the depth squared. So we need to know what the depth and the depth squared is initially. And then when we do all our averaging and such, well, then these will change, and then our variance will change, and, so forth and so on. So yeah. And in fact, right now, if I build and run, since we are just writing our basic depth information to our shadow map, this should work just like before. So yeah, now we have PCF soft shadows, except they're being sampled from a variance shadow map. So there you go. But of course, that's not what we're trying to do. So let's go to our sampling.glh. And actually, let's also go to our lighting main shader. There you go. And let's add new function. I'm going to copy just the basic sample shadow map function. I'm going to rename it Sample Variance Shadow Map. And I'm going to use our new function here. So, there we go. And because I'm paranoid, I'm going to build and run one more time. Because, see? You got to make sure you're using it correctly. So, yeah. Something isn't working now. Which actually doesn't make any sense, because... Oh, I know why it's not working anymore. For one, we don't need the texel size anymore, and actually, we're also not going to need the bias anymore, so yeah. So I'm going to actually delete those. So we've gotten rid of the last parameter, and we've gotten rid of subtracting the bias, so we're using unbiased depth coordinates now. And we're not going to take those in there anymore either, so we should just have basic shadow mapping now. Glorious shadow acne, all the artifacts, and everything. Great. So now let's change things, and let's actually implement a variance shadow mapping, thing here. So, here's how you sample a variance shadow map. The first thing I'm going to do is just comment this out. I'm not going to delete it because it's actually going to be useful in a moment, but for now I'm just going to comment it out. And the first thing I'm going to do is I'm going to sample the variance shadow map. I'm going to store it in a vec2 I'm going to call moments, because, there are moments of depth. So, in fact, I'm just going to copy this line and change it from .r to .xy. So there, now we have our depth and our depth squared from the shadow map. So cool. Now from this, there's two things we want to calculate. The first off is some float I'm going to call p, because, well, that's what it is in the equation. And this is going to be the value from our shadow map. So essentially this is doing exactly what this line of code used to do. It's just now for our moments variable rather than the shadow map. So it's going to be step with compare and moments.x. So there. This is what our value would be if we're just sampling it from a regular shadow map. That's the first thing we want to calculate from our moments. The second thing we want to calculate from our moments is the variance. Because remember, we're not actually storing the variance in the variance shadow map. We're just storing the information we need to calculate that. And here's how we do that. What we're going to do is we're going to take moments.y, so remember that was our depth squared, and we're going to subtract it, and we're going to subtract from that, I should say, moments.x squared. So moments.x times moment.x. And you might think, well, since moments.x is the depth and moments.y is the depth squared, shouldn't this be 0? And yes, right now, this will be 0. And in fact, that's bad, because we're about to do an equation involving dividing the variance, and well, we don't want to divide by 0. So, what I'm actually going to do is I'm going to do a max here. I'm going to do max of variance and a really small number, 0.00002. I found this, just from my experimentation, I found this is usually a good value, but eventually we're going to make this uniform, so you can make it whatever you want. If this doesn't work for you, again, you can play with it, you can get rid of a 0, you can add an extra 0, but I'm going to add, I'm just going to have, like I said, this. So cool, we got the values we care about. We know what our value would be just from a basic shadow map test. We know whether this, in a binary representation, whether this pixel happens to be in light or happens to be in shadow. And we know variance. We know, again, in this case, it's going to be whatever this constant is, but later on, it's going to matter. So here's how Chebyshev's inequality works. What we need to know is we need to know the distance from the mean. So the distance our compare value is from moments.x, because moments.x is, supposed to be the average. And we can calculate an upper bound like this. We are Pmax, the maximum percentage of values that are greater than or equal to, our compare value, is our variance divided by our variance plus our distance from the mean squared. Okay? So if our compare is exactly equal to the mean, then the maximum percentage is going to be 1, because, worst case scenario, all values are exactly equal to the mean, so, there. Well, that's how that works. And of course, if d is 1 standard deviation away, then Pmax is going to end up being 1/2. Because, at most, 1/2 can be greater than or equal to, and still have the variance be valid. So, that's sort of how that works. It's hard to give... I think it's a little hard to get a really intuitive grasp of exactly how that works, but, that's sort of how that works. So, yeah. So now we know the upper bound, the maximum percentage of values. So what we want to return is, we sort of want to return Pmax. But what we want to do first is we want to actually take a max of P and Pmax. Why? Because if this pixel happens to be entirely in the light, then P, in theory, should be 1. So this way, this is just a nice little check to make sure we're not returning some probability of, oh, it's actually fully in light, but it's partially in shadow, because there's that oddball chance that something could be off in the variance. But no. This way, if it is fully in light, then we're taking the max of 1 and whatever that is, and it'll always be 1. So there. And also, there is the chance that Pmax ends up being more than 1 somehow. I'm not actually entirely sure if it's possible in this configuration right now, but some of the changes we're going to make later, I definitely know will make it possible, so I'm going to take a minimum of that and 1.0, just to make sure this doesn't exceed 1. And there, that should give us basic variance shadow mapping. So let's build and run. And hey, what do you know? We've got our lovely aliased shadows back. Now notice, this has actually solved the shadow acne problem. So we don't have any shadow acne anymore. But we still have that aliasing. So how do we deal with that? Well, here's the thing. What we ultimately need to do for this whole variance shadow mapping to work properly is we need to have some average depth at every pixel. Now, of course, right now, we don't have that. That's why we have these razor-sharp shadow edges. But what we can do is, well, what happens if we change the filtering to linear? Now, normally this wouldn't do anything because, well, in basic shadow mapping this wouldn't do anything because we'd be, ultimately doing a binary comparison. And if we have linear filtering, we're having some average, and that doesn't matter. But this variance shadow mapping, that's all about the averages. So if we're averaging the depth like this, well, you notice we're getting soft shadows now. Because again, variance shadow mapping is all about averages. So when we do the linear filtering, that's averaging the values. And, well, that, in effect, that softens our shadows. Because that is giving us an average. It's not giving us average everywhere, it's only giving us an average, in those values between the, light and shadow, but it's still giving us an average somewhere, and therefore, we're getting some nice filtering from variance shadow mapping. So hey, so hopefully you see something kind of interesting here. Now, because we're dealing with averages, all the hardware filtering stuff that ultimately deals with averaging values works for us. So we can enable anti-aliasing when rendering the shadows, and we'll get anti-aliased shadows. So that's one thing. We could enable, say, anisotropic filtering and MIP mapping and such, and that'll make shadows look better when they fade off in the distance. So that, in and of itself, makes variance shadow mapping a really, really powerful technique. Because now, all of a sudden, all the hardware filtering tools work. So, yeah. And that, ladies and gentlemen, is how you implement basic variance shadow mapping. So, thank you. Hope you enjoyed. Hope you learned. And I'll see you in the next video, where we're going to be talking about some of the artifacts that come along with variance shadow mapping, and how you can overcome them. And yeah, that'll be the topic of the next video. In the meantime, if you feel like playing around with variance shadow maps a little bit more, there's a few things you can do just as personal exercises, just to play around with things. For one, I already mentioned how all of a sudden all the hardware filtering tools are available to you now. So you can try enabling MIP mapping and anisotropic filtering, just things like that, and seeing how it affects shadow map quality. Another thing is, our shader already has code to sample from, to sample with percentage closer filtering, so you can try using percentage closer filtering using variance shadow mapping as your sampling function. And that can do some interesting stuff. And in fact, if you get that working, even that by itself reduces the cost of PCF by a factor of 4, approximately. So, yeah, this is really good for that. Granted, in the video after next, we're actually going to see there's an even better way to filter variance shadow maps, but hey, if you want to play around with things, that's something you can do. And if you're feeling particularly adventurous, you can try enabling anti-aliasing when you render the shadow maps. And you'll notice, even that by itself will give you anti-aliased shadows. So, that's something interesting you can play around with. And I say you have to be adventurous because, well, our engine isn't exactly designed to have anti-aliasing just yet, so you might have to play around with some of the frame buffer creation code and whatnot, but hey, if you feel like doing it, it's interesting. So yeah, those are a few different exercises you can do just to play around with things if you like. But other than that, folks, thank you. Hope you enjoyed, and I'll see you then.